Welcome to part 2. The model reads a chunk of text up to 1024 tokens at a time. Same context window GPT-2 used, and for every token in that chunk, it guesses what comes next. Cross-entropy loss, also called log likelihood, is just a score for how good those guesses were. Confident and correct, low score. Same idea as perplexity from paper 2, it's just a different name. Average the score across the whole 1024 token window, and that's loss. To give it a scale, it's measured in nats per token. And in this paper, the number run from around 6 for tiny models down to about 2.45 for the biggest. Of course, the authors checks loss on web text too, but they also check loss on other kinds of text the model wasn't trained on. That's the transfer question. Does loss on the training distribution predict loss somewhere else? Almost everything they train is a decoder-only transform, same family as GPT, but they deliberately also train some LSTM models and something called universal transformers as a comparison group. That's how they can confidently say architecture barely matters. They tested other architectures side by side and scale still won. Now let's talk about 2.1. We are going to see three things quite a bit. N, C, and D. N is model size. Now the paper here is saying how to calculate it. Now think of N as it is measuring the recipe cost. You count the flour, the eggs, the butter, but not the number of labels stuck to your pantry shelves, which we are calling the embedding table. The embedding table, the layer that turns token IDs into vectors, is more like a entry label. Its size is set by how big your vocab is. It has nothing to do with the size of the model. So it has no impact to how much the model can actually reason. So N is defined as a non-N parameters only, so that we leave the vocabulary size part out. And the scaling line essentially depends on reasoning part. Second, dataset size D, number of training tokens C, and of course, third is compute C, roughly 6 times N for every token. Here's where that 6 comes from. 2N flops per token for the forward and 4 flops per token for the backward. Now, why 2? Every parameter touches the token once. One multiply, one add. 2 operations per parameter, so a forward pass is 2N. The backward pass costs roughly twice the forward pass. And you add them up, about 6 times N per token. Now, think of cost per token times token trained on, and we get the famous C equal to 6ND. The paper writes it as N times B times S. But essentially, batch size times the number of steps is just the total tokens the model processes. Apply this formula to a real-world example. In GPT-3, C equal to 6ND. Here, N is the number of parameters, which we know 175 billion. We know the dataset size, which is 300 billion tokens. And together, this massive number of flops. Now, from flops, we can figure out how many GPUs were needed, around 1,000 GPUs for around a month. Now, it would be good to define what is the forward pass and the backward pass. The forward pass is the guess. The model takes the text so far, runs it through every layer, input to output, to predict the next token. Each parameter fires once. One multiply, one. You can call it 2 operations per parameter per token, which is what we saw in the map. The backward pass is the learning. Once the model sees how wrong the guess was, it walks the layer in reverse. Output back to input, and asks for every single parameter. How much did you contribute to that mistake? And which way should I nudge you? That's the gradient. And it costs about twice the forward pass, roughly 4 operations per parameter. Because at each layer, you compute 2 things. The error to pass further back, and the correction for that layer's own weights. Now look at this graph, which is loss versus model and dataset size. Now the early stopped test loss, L here, also varies with the dataset size and the model size. So you can see a larger model trained before convergence would do better than a smaller model trained till convergence. As you can see, a smaller model, you train till convergence, the loss still remains high, while a larger model starts dropping more quickly. Now, this graph is really important. First, let's understand what do we mean when we say a frontier model. A frontier model essentially means that for a given compute, we have the lowest loss. It means no other model can achieve a loss lower than that. So that is the goal. Now, in this graph, you can see the loss function is on the y-axis, and then here's compute, essentially how much budget that you put in. Now, what it says is if my compute budget increases, there's a particular relationship. Roughly, you need to increase n more and you need to increase d less. So the n increased to 1.2 trillion. N is essentially how large the model is and how big the data is. And data just moved from 20 to 140 billion. So let's say if you go to the midpoint, we see it scales from 15 billion to 1 trillion versus the D did not scale as much. In essence, what this paper is trying to say is that given more compute, spend most of it on making a larger model, don't need to get the more data. Now, this was challenged by the Chinchilla paper. We use a smaller model with more data, and that gives us a lower loss. So in essence, this paper was superseded by Chinchilla, who proved the frontier to be lower than Kaplan. So that is what the graphs show. Loss against compute, loss against size, and the correction Chinchilla made later. That half is behind us. Now the three claims, and as an engineer, this is the part I came for. Now, before we get to the FAQ, let me boil the whole paper down. Essentially, this paper has three big claims. At the time, all three were controversial. And that is why this paper was so important at the time. Claim one, convergence is a trap. So let's say you take a fixed compute budget. You would think the safe move is to pick a small model and train it until the loss stops dropping. The paper says no. Spend that same budget on a bigger model instead and stop it early, long before it's done. The bigger model will still come out ahead. It's more sample efficient. It means how much a model can learn from each token it sees. A more sample efficient model gets the same amount of learning out of fewer tokens. So it gets further on the same compute. Training a small model to the finish line just burns the budget, as per Kaplan. Claim 2 is when you scale up, you grow the model faster than the data. Extra compute should go mostly into parameters and only a little into extra tokens. That's what Kaplan had to say. You do add data, just nowhere near as fast as you would add size. Make the model a lot bigger, data set a bit bigger. That was the recipe. It's also one of the things that got challenged later, and we'll get that into a bit. Now, coming to claim 3 is you can see the future from small runs. The loss falls on a straight line on a log plot, and that line goes across 7 orders of magnitude. So you don't have to train a giant model to know how it will do. You fit the line on small, cheap experiments and read the answer straight off it. Roughly what it will cost, roughly what loss it will hit, you'll be able to answer before you spend money on a big run. That's the part changed how every lab plans. Now let's get into frequently asked questions. Our first question, how do Kaplan, the 2020 scaling laws relate to Chinchilla, the DeepMind 2022 paper? Now, Chinchilla didn't overturn this paper. It did correct a number in it, and that number is important here. Kaplan's recipe was model heavy. When compute goes up, pour most of it into a bigger model. Essentially, 10 times the compute meant about 5 times the parameter, but less than double the data. 2 years later, DeepMind's Chinchilla reran the experiment more carefully and found Kaplan had undertrained on data. The optimal split is close to balanced. Grow the model and the data together. The proof was blunt. A 70 billion parameter, Chinchilla beat the 30 billion gopher at the same compute. Smaller model, more data, lower loss. Around 20 training tokens per parameter. But a lot held up as well. The whole method, the power laws, C equals to 6ND, predicting big runs from small ones. Chinchilla used this exact framework to find its answer. It just refined the split. Now to our next question. We talked about model size and data as if there's a trade-off. Why is there a trade-off? It's a trade-off because of our formula, C equal to 6ND, ties N and D to one fixed budget. Compute is roughly 6 times N and D. Now, N is how big the model is, D is how many tokens you train it on. If you make the compute fixed, the product is locked. So the two numbers seesaw. Every extra parameter you add has to be paid for with fewer training tokens. Every extra token means a smaller model. Now, you can't grow both for free. A bigger model on the same budget means less data. More data on the same budget means a smaller model. The budget forces you to pick the split. Best way to think about it is, given a fixed bill, would you invest on a bigger brain or would you invest on reading more? On to our next question. Do scaling laws mean we just need bigger GPUs forever? In 2020, that was a strong read. Bigger GPUs, bigger models, better scores. By 2026, the story has some caveats. It's like sprinting. The 2020 view is fastest runners always win. 2026 view is yes, but also there are other things like diet, coaching, strategy that matters just as raw leg speed. We now know data quality matters enormously and not just quantity. Post training makes a big difference, and that's essentially the coaching. It's the stage after pre training where a model gets fine tuned on human feedback. Things like reinforcement learning from human feedback and instruction tuning. Test time compute is a newer scaling axis entirely, letting a model think longer with reasoning chains and tool use rather than just being bigger. Synthetic data, text generated by other models and fed back in as training data, also changes the story around data. But the core Kaplan result still holds underneath all of that. Loss falls predictably with scale. The field just found more dimensions worth scaling along. Next, does lower test loss means better downstream task performance? Generally, yes, strongly correlated. If you design your test loss well, it's generally very strongly correlated for generative tasks, perplexity-driven benchmarks, and zero. But think of it more like a thermometer. Like it usually tells you whether your steak is done. It does not tell you whether it actually tastes good. Now, this is part of the why the paper matters. Loss is cheap and automatic to measure. Performance is expensive and depends on which benchmark you pick. Is a model's loss comparable across different labs? The loss number is basically lab specific. You can't line up OpenAI's loss against DeepMind's and read off whose model is better. There are two reasons. First, the tokenizer. Loss is measured per token. How surprised the model is by the next token. But different labs have different way where they chop text into tokens. Some labs might have a different strategy than the other. Second, the dash set. Loss on Wikipedia isn't the same as loss on Reddit or isn't the same as loss in code. And that is why this paper checked loss in multiple different data sets as we had explored. Now we come to the end. Paper 1, attention, gave us the architecture. Paper 2 gave us the pre-training thesis. Paper 3 essentially gives us the engineering economics on how to project coaching. Thanks for listening to this paper. Let me know if you would like me to read other papers. I will see you in paper 4.